My name is Maximilian Trescher. I'm a machine learning scientist at dida. And as David already said, this talk is based on a project we did at dida. And let me introduce it visually. Imagine you have pictures like this, or rather videos like this, where you mounted the camera in the front of a train and you're driving on the tracks. And now you have hours of videos of a train driving on a track. But imagine you want to find interesting scenes where the video doesn't look all the same all the time, but you want to recognize occasions where there's something new, interesting, or dangerous happens, like a giraffe crossing the tracks. Yeah. Okay, I admit it's a very unlikely thing to happen here in the mid of Germany, but that illustrates exactly the point of this project. So we want to detect things that we have not seen before. Okay, so we don't have like classes of objects that we have lots of labels for, but we want to detect anything that happens. And as David said, it was a project we did together with DB, and I'm happy to welcome even some of our project partners from DB here today. And I also want to make the project statement or the goal statement more formal now. It was said that we should, it read like here on the slide, objects within the volume surrounding the upcoming parts of the train should be detected, or must be detected. And the potential object types are unknown. So that's what I said when I called this talk Detect the Unknown. Here there's also already a disclaimer from my side. It's not only a hard problem to solve, but it's also hard to evaluate in the end. So you won't see many fancy metrics with very high accuracy numbers today. I'll show you some examples, try to explain what we achieved, but just so you know. Why are we doing this? Well, the long-term goal, of course, for Deutsche Bahn is to develop partly or fully autonomous trains. But to put this into context, this is not what we're trying to do right now. We're part of an ongoing research and development project, right? And we're focusing on a proof of concept and exploring different possibilities. I'll present like some part of what we did here today in a focused manner, and we explored some more possibilities also. And the main goal for now is actually to narrow down the huge amount of data that Deutsche Bahn can collect by putting these cameras to find, to more easily find the interesting scenes and the long times of videos, or the scenes where you can train subsequent projects on. What will be in this talk? There are 3 highlights I want to mention. First, I'll talk about the dataset, which is actually by now publicly available. Later on, I'll present the architecture that we settled on in the course of this project, and I'll go through the items in this architecture step by step. And one of these items is the monocular depth estimation, and I'll spend some more time there because I think this was a real highlight, and I like the concept of these models so much. And in the end, as promised, I'll also show some results. So let's start with the dataset. The dataset we worked with is called the On-Sensor Data for Rail 2023, or short OSDAR. It consists of 45 scenes, different scenes that are recorded at a frame rate of 10 frames per second, and that collect a number of sensors. So it's not only a single camera, it's multiple color cameras on a train. It also includes data from infrared cameras, lidar, radar, localization like GPS, and EMU, which means acceleration sensors. There's a paper about this data set. There's a URL where you can download all this data, and it's released under a CC by SA license by now. We are only working with the color camera images in this project. I'll talk about the lidar on one slide again. So lidar is distance measurement by lasers, right? And this dataset also comes with labels. So this is nice. Of course, we like labels, and these are labeled by humans, and we didn't have to do it. And you can download it and have the labels as well. But I want to show you also the class of labels that are here and the types of labels. So we have, for example, polylines for the tracks. We have, lines, then we have polylines for this like shape of bigger objects like the train, and we have bounding boxes for some types of objects like persons or signals and so on. And on the right, you see a list of all the classes that are labeled in this dataset and the number of occurrences per class. So I won't go through this in detail. There's a lot of signal poles, for example, not so many bicycles. But you also see that there's a limited number of classes. So there's not really much we can do with these labels to assess whether we can detect everything that will be there. I'll come back to the labels later when I present the results. But okay, I said we want to discover objects that are not part of these classes, and how are we going to do this? For this, I'll want to walk you through the architecture of our system now. We use an algorithm that consists of 4 steps, basically. And the 3 on the left include deep learning models to some extent, and the one on the right is just purely putting everything together and applying some, I say, regular logic to make it work. So on the left, for the deep learning steps, we have the ROI detection, that means region of interest detection, based on a track detection. We'll do some depth map estimation or distance estimation and an image segmentation. And all these arrows mean that we feed the output of the one step into the other step. Of course, they all should go into the final result. And on the connection of the depth map to the image segmentation, I'll talk about this later in more detail. But let me start with the ROI detection, because actually I'm not going to talk about this very long. The project said we should detect objects within the upcoming path of the train. So this means we should follow the tracks, right? Luckily, well, I said this dataset already has labeled tracks, but of course, this only applies to this dataset. But DB also had a finished solution for detecting tracks. And so from my point of view, this problem was solved, and they could just use it, get the track lines in the images, and all we did is select the correct tracks, which are the central tracks on the bottom of your image, and then follow the lines. One more caveat. We want to detect unknown objects, and if you limit yourself to just the tracks and just the scenes that DB already labeled or recorded, then there's not so many dangerous things on these tracks. So in the end, we loosened the restriction on the region of interest and said basically we will look first at all of the image, and then we say we could, of course, if we want to restrict our algorithm to the region of interest. But later I'll show results like for the full image. So with this, I can come to the next step. Estimating depth maps or distance. And I'm sorry if I use these 2 terms interchangeably, but they really mean the same, depth or distance for me here in this context. And the problem is called monocular depth estimation, where from a single image, you want to assign to each pixel a distance value, like the distance from your camera to that object that is depicted on the pixel there. This is also the third highlight I announced, and I'll spend some more time explaining the training and fine-tuning of this model. And to make it less abstract, I want to revisit my giraffe. We have this image recorded by a regular camera, and we want a model that gives us a depth estimation, a distance estimation, as I said, and here represented as a color map. So yellow means it's very close, black means it's very far away. And in this distance map, I can clearly see that there's some object standing up from the ground. So that is really why we do it. We want to detect objects that are sticking out, that are potentially somehow blocking the way, right? This problem, of course, if you have a 2D image and you want to make it 3D, basically by adding distance, is mathematically not well defined or not in a strict sense solvable. But with deep learning, you can actually do very good guesses. And that's what I want to show. So we used a model that's called mono-VAT. It's mono for monocular depth estimation and VAT for vision transformers. I'll later say something about vision transformers as well. It's a pre-trained model. It's available at GitHub, and there's also the references linked. It's in turn based on monodepth too, and I mention this here because the people of monodepth are actually the ones that introduced lots of the interesting ideas to this field. Mono-VAT is pre-trained, so you can just use it and you get a depth map out of it. And it's pre-trained on datasets from driving cars. So probably some of you have heard of this Kitty dataset. It's used like everywhere. So this is useful, but we can even do better, and I'll show you how. So first, I want to show you the full model structure of MonoVIT, and please don't be afraid, I won't go through each of these blocks here. I just want to mention the overall structure. So actually, MonoVIT consists of two deep learning models that are trained together. The one on top shown here is the transformer-based depth network. So that's the one that's actually doing the depth estimation. You give one image in, you get a depth map out. And it has this familiar unit shape, it uses transformers, whatever. The important thing is there's this part of it, and then there's a second network down here, the pose network. And this one takes pairs of images and estimates or tries to estimate how much the camera moved in between the recording of these two images. And then by some clever tricks, you can use these two networks together to train it in a self-supervised way on video recordings done with a single camera. And I want to explain how this works so that you can believe it. Let's start simple. Say you have a camera, and this camera takes a picture of a cube here. Then in your image, shown here the frame A, the image the camera recorded, you'll see this cube at some position. So you know the angle of where this cube is in space somehow, but you don't know like what's the distance, right? That's what our depth model should give us. Now, if we mount this camera on a moving vehicle and start recording a video, what happens? Well, after some time, we record a second frame in our video, like the tenth of a second. Our vehicle in between moved a little bit. That's meant by this vector m here. And then our frame that we record looks a bit different. So we moved closer to the cube in my example. So it changed the angular position. Of course, it also changed in distance. It now appears bigger in the frame B. So what did we get from this? We have two frames recorded. And we have two parts of our network. And I mean, they are already there. So in training, you start out with some predictions of your network, and then you refine them, right? So what do we have? We have the pose estimation that, given these two frames, gives you an estimate of how much the camera moved in between. Now, we also already have our depth model. Okay, we want to fine-tune it, but it's already there, so we know like the prediction for the depth in the first frame. Now, if I combine the first frame and the depth estimation, I can make it a 3D point cloud, basically. And then, if I know how much I move my camera into this 3D picture, I can calculate how the next frame should look like, right? I know the distances, I know how much I moved, so, well, there's some geometry involved, but you can figure it out, and then you'll get a predicted frame B. And you also have the real frame B. And, well, you compare them, and in the beginning, your model is not perfect, so there will be a difference. And what you're trying to do is to make your model so good that there's no difference in the end, right? That your predicted frame B will be like the real frame B, then both your pose estimation and your depth estimation are correct. So you have a difference here, and you're trying to minimize it. That sounds a lot like a loss function, right? And that's exactly, or more or less, what happens. There are some more terms to the loss function in the actual model, but basically you're trying to minimize the difference between this predicted and the real frame B. And okay, now I'll come back to the model, and I hope you now understood why we need the two parts of the model, and that together we can train them in a self-supervised way, which means we don't need any depth or distance measurements or labels or so on. How does that help us? Well, the MonoVIT model is trained on this driving car dataset, and it gives us okay results. But by fine-tuning it on a lot of data that looks exactly like our data recorded from the front of a train, we can improve it a lot. And I'll show you just some results. So we did this, right? We fine-tuned MonoVIT. Before our fine-tuning, just the pre-trained model gave a distance estimation like this. I hope you can see it with the lights. There are a few problems, like this wall here, it has graffiti on it, and somehow the contrast of the graffiti results in the model to predict that this graffiti is really 3D. It's not. And also the contrast, the edges are always a problem. Like here the wall has some connections, and they are also in the depth, they are like sticking out of the wall. And after fine-tuning, you see that the wall gets nice and smooth. It's just a wall going into the distance. And the pole here in the front is actually in front of the wall by a bit. Just for you to compare it again, like here the wall was noisy and somehow 3D, and now it's a smooth, flat wall going into the distance. And I have another example, also for the platforms. It's again mostly a problem with the bright edges of the platform that somehow it's a bit hard to see, unfortunately. So there are more white lines here, and they are also sticking a bit out, like in distance. They get less distance somehow. And if you compare the two, you can see, well, you can't really see, right? All right, here in the corner you can see clearly. So there was this platform before, and this part is close to you, and this here should be further away. And after fine-tuning, it's actually further away, and some of the 3D shape of the platform is captured better. And what you can see barely here on this projector is that also the structure of the house in the background is captured in a better way. Now you have to believe me somehow. It's a house, but it's open in the front here. I don't know how hard this would be. And then here, after fine-tuning, you can actually see that you can go inside, basically, that's open here. And that the trees are actually further in the background and so on. So the result is basically it's much better after fine-tuning. So now that I explained the depth estimation, I want to come to the next step, which is the image segmentation task. For this, again, we use a pre-trained model. It's called Segment Anything model, or short SAM. It's a huge pre-trained vision transformer by Meta. And what's special about this is it not only gives you segmentation masks for, well, any image as they claim, but that you can also prompt it with texts, with points in the image, like coordinates, or with bounding boxes to pre-select kind of what you want to segment. And here I linked also the original paper and the website where you can try segment anything on your own images. Let me do a short interlude on vision transformers. It's just one slide for people who know about transformers a bit, and maybe CNNs a bit, never thought about vision transformers. So the others, please bear with me, and I'll be back on the next slide. So how do vision transformers work? Well, the idea was basically that these transformers for large language models and general NLP tasks work so well, so we wanted to use them for images as well. But how do you do it? You take an image and you cut it into like small patches. And then what you do is you take these numbers that are in these patches, they're just RGB or whatever, and you put them in a flat array. It's a long 1D array. And you learn some linear projection on this as well and add some position embedding. But basically, you're just giving this in a long 1D array, all these patches, and feed them into a transformer. Also, this position embedding doesn't include any 2D information. So in the beginning, the model doesn't know anything about like how these patches are arranged. It's just about to learn about this geometry by itself. And well, surprisingly, this works really well. And once you did this, you have a sequence of like long 1D embeddings, and that's exactly what a transformer works on usually, right? So, well, usually you embed words or tokens or whatever, and then you feed in sequences, and then you can transform, then use the attention blocks and so on. And that's basically what a vision transformer is. So SAM is a huge vision transformer trained on a huge data set. And in this case, we just use the pre-trained model as well. So what does it do? It produces high-quality masks of objects. It looks like this. If we feed some image, this one here, into segment anything, you will get all the objects in the image basically segmented. Of course, you can debate, like, is this one object, is this two objects? You'll get some segmentation of the image. But what we really want to do is detect dangerous objects or objects that are sticking out of the ground, somehow obstructing our path. So what we try to do is use the depth map to help segment anything, to only select the relevant images. So we used interesting points on the image, and in our case, that's the local minima of the depth map, right? Something that is close, and somehow around it, everything else is further away, so there's something sticking out, and this is the point I pass to segment anything. As I said earlier, I can prompt it with coordinates in my image. And what then happens is I have, well, the general segment anything, I'll have my depth map, and then I'll end up only having, I hope you can see it, a few objects segmented here. And this now looks like we are close to what we actually want to do. So we selected persons, we selected a sign here, a sign there. As I said earlier, for now, I won't restrict myself to the region very close to the tracks, because usually it's free. So I'm looking for any object that could potentially be dangerous if it's close to the tracks. And, well, I selected a few of these objects. And that already brings me to the last part of our algorithm. This is selecting relevant objects. Now, I showed you what we all did, and now we have a selection of objects, and we could apply the ROI filtering, which I won't do. We could use more information from the depth map about a single object. So, we have the depth maps available, and that means we can, the single segmented objects turn also into 3D objects, basically. And we can see if they are more flat or if they extend into large volume in 3D space. We can filter the masks, for example, to filter out things that are too far away or very close or too small, or that are like very large if we want to exclude buildings. But this is just really like all these filtering options are more meant to be an option for using this algorithm as a toolbox and then to see what happens. Basically, what I'll show you is the more or less unfiltered version of it. And this already brings me to the results. So I'll show you some results here. And what we have is some images out of this OSTAR dataset. And it has some labels that come with it. So this is the blue boxes. And I have to say, we're not trying to recreate the blue boxes, right? We are trying to detect like objects that are somehow in the way. And then what you can see is that somehow, of course, we also detect some of these signals that are very clearly sticking out of the ground. And well, what did I want to mention here? We detect some of the interesting signs. We don't detect the poles in the distance so well, and sometimes there's problems that we also detect the tracks. There's things we could potentially improve, but what is nice is that we detect these small, like here's a small box next to the track. I mean, this should be here, right? So this size is probably uncritical, but our algorithm said, okay, wait, there's some object next to the track, and it's pretty much featureless. It's just a box. And here's another example. So here again, well, okay, there's things we detected here on the ground that is not so interesting, but actually we captured quite well the person on the platform. We captured the signs that are somehow moving into our image. And I can show more examples that here, this is the example we had before for the image segmentation where we detected persons and again some signs. And all this is basically to say, this is different from your object detection that you usually do where you define classes and then you find these objects again. This is really, okay, we are trying to find whatever object there is. And here again, we find lots of these, well, here's a sign that's clearly visible, but then again, there's more or less featureless white boxes, and that always made me think of the people from Deutsche Bahn that told us once they saw a fridge on the tracks, and that's basically a featureless white box you want to detect. And yeah, that's basically the result, the state of the algorithm as it is now. And there's also a second result, kind of a side result of this thing, is that fine-tuning mono VIT is actually quite helpful. I told you earlier that they also recorded lidar data in this data set. And so we can compare our depth estimations to the actual lidar measurements on some points, right? And what you see is that, well, of course, it's not 100% perfect, but it correlates quite well. And there are some problems with noise and with the edges of objects and so on. But well, the takeaway is it works so well that you probably, at least for some use cases, you can just get rid of the lidar and use the depth estimation. That brings me to my conclusions already. We had many more ideas to explore. I just told you about 3 steps in the pipeline. I missed to mention, like 20 minutes ago, that we also explored clip embeddings, optical flow, whatever. If you're interested in this, please ask me now or later. Our result is we were able to detect a lot of previously unlabeled objects and also find some of the labeled ones again. Also, as I said, it's hard to evaluate in a numeric manner. For complex problems, I'd say there's no out-of-the-box solution, but combining different out-of-the-box solutions is quite powerful. So we took 2 pre-trained models, right? Applied some fine-tuning, some clever combination of them, and that helped us developing a final solution. And then there was this actually very valuable insight for Deutsche Bahn that maybe they can just use the monocular depth estimation in a fine-tuned way, which they can do cheaply because they don't need labels for fine-tuning it, and use it on instead of the lidar system. With this, I'm nearly at the end of my talk, but I should mention that, of course, I didn't do all of this work alone. That's the team. There was Will, Marley, Marty, Konrad, Jona, and me involved, and thanks to all of them. And with this, I say, let's detect the unknown, and in the meantime, I hope I can answer some questions.
Great, thank you. Very interesting. Do we have the first questions?
It should be very difficult to for moving objects, or let me say for a bird. So it's flying, for example, in the direction of the train, and you have no idea of how fast it is. So, so can you detect a bird? So,
well, the model we have works on single images for now, right? And at this stage, it wasn't meant to work in real time. So it's really just, at this point, a development tool, basically. So what you could do is, well, you detect objects and potentially birds, if they are large enough in a sequence of frames, and then you could see that they are moving, and then you could also track their distance, maybe.
Yep, another question.
For the talk, I was wondering if you also compare to other methods. So do you evaluate on a test set, or do you only look at test like final results?
It's a good question, and yes, you should look at a test set. But the point was somehow, well, we had no test set where it was well defined. This is what you should detect, and this is what you shouldn't, because somehow the point of the project was to, well, detect the things that were not yet seen there. What's made it so hard. So we mostly looked at things, and this is also why we tried more algorithms, and we looked at their results and said, well, this looks promising. This one, not so much. And this is how we settled on this, basically, in the end. I mean, we computed some metrics to say, okay, how many of the signal poles can we find? But then the question is, okay, if you can find all the signal poles, is it actually what you want or not? So.
Okay, thank you.
I just wondered to this, did you think about maybe data augmentation and creating your own like weird things on the track and seeing how well your model works?
Yes, well, we thought about it. We definitely talked about it multiple times if we could somehow generate 3D models or like put it on the tracks. We didn't in the end. Now for the talk, for visualizing, I just copy-pasted this giraffe there, but I know we were afraid that it's too obvious to the models that they would learn somehow the artificial things then, so we didn't. But it's an interesting idea in any case.
So
After working on this project, did you discover some other ways you can apply what you just finished working on, other maybe ways, industries, or any other place you can apply the same things you learned doing this project?
Well, it's an interesting question. I think the combination of these two things was specific to the project. I think for us the learning was really that for me it was the first time working with a self-supervised learning model, and I was like happy that it actually works because it somehow feels self-referential all the time. But then you see in the end that this works. But no, there's nothing specific I could say that we want to apply this to.
Could you say a few words on the technical side? Oh my God. A fine-tuning step, like when you did this depth fine-tuning? And second question, how long did this project take from the beginning till the end?
Well, let me answer the second question first, because that's a short answer. It was 2 times 3 months, and I say 2 times 3 months because it was some stage in between. And then like a few people, like you saw 6 people there, right? There was 3 people and 3 people, basically. For the fine-tuning, I'm not quite sure I understand your question, like what kind of technical details you're interested in. I mean, we took lots of these images, these videos, image sequences we had, and then, well, the model is already done, right? So it has a training routine. So we somehow connected that and made it run. For the actual very fine details, I'd have you to connect to my colleague Marley, who did the fine-tuning.
Thank you. Looking forward, would you predict these systems will ever have a high enough accuracy to be used in a production environment? So let's, hypothetically speaking, Deutsche Bahn gives you 100 million euros. I mean, obviously, you want to avoid too many false positives, right? If there's like a buzzer going off and the train conductor has to silence it every like 5 minutes because of a false positive, it won't work, right? And that will be the critical bottleneck of like, can you really, really push the accuracy to a point where this is useful in production?
You're basically asking if it's going to be fully autonomous, right? And so
like a judgment of how you see the potential, assuming you have like an unlimited amount of resources or 100 million or whatever you need, you know?
You're putting me really on the line here, and there are even DB people in the audience, so maybe we could shift this discussion to the coffee break. I'm afraid of saying something that they don't agree with.